Okay, then let's start this class. Yeah. Yeah, I have already uploaded the lab 5 instruction. I don't know if you check it. Yeah, today we will talk about the discharging capacitor. And before we talk about discharging capacitor, and let's talk about what we have already did, we have already done. Yeah, actually, we have already learned something about onboard ADC, am I right? Yeah, we have already finished the lab 4. It's onboard ADC. And actually, this is what we have already done. This is like a potential meter, am I right? And the resistor will be changed when you adjust the button thing like that. And you can see actually this circuit can be transferred to this one. When you adjust the point, the R1, R2, the resistor value for R1, R2 will change. And then the voltage will change because the resistor changed. That makes sense to you? And then what you read actually is this point, the voltage, am I right? How can you calculate? You use this equation. We have already talked about that, am I right? Yeah, the total is 3.3. And this is your read data, and this is the total, am I right? And then you can use this equation to calculate the voltage, the output voltage, this point's voltage. Yeah, you have already finished this one. That makes sense to you? Any questions so far? Okay, and then we know if you check your code, and the onboard ADC is the possession is 16-bit. Am I right? Yeah, but we will talk about that later. And the decimal number will be 0 to 16,535, like that. Yeah, you have already finished that and tested it. And any question so far? No? And then this is the voltage you from this point. And you can see the total, the minimum will be 0, and the maximum will be 3.3. Am I right? Yeah, if you finish that, which means that the minimum binary will be decimal will be 0, and the maximum binary decimal will be 16,300, like that. Am I right? Yeah, but in the real circuit, maybe the value is not that, it's not like absolute 0 or absolute 16,500, like that. And but this one 3.3 divide 16,500 is just a 1 unit, just like the minimum resolution. Am I right? Which means 1 unit is how much voltage. Am I right? Which means when you read 100, this is your voltage. Am I right? Output. And when you read data is 10,000, and this is your output voltage. And if your read data decimal number is this one, and this is your output voltage, you know that, am I right? Any questions so far? Okay, let me ask you a question. Pico W ADC is 12-bit or 16-bit?
I'm sorry. Oh, it's 12-bit.
Yeah, actually, the Pico W ADC is not like a 16-bit. It is 12-bit, which means the hardware ADC resolution is 12-bit. It is like a 96 levels. And the voltage range is the same thing, 0 to 3.3, which means the resolution will be around 0.8, like a millivoltage per second per step. It's not like a 0.0005. Yeah, but the micro pattern, if you check the code, it read like a 16-bit. It returns 0 to 65,535. Yeah, because like the micro pattern scales 12-bit value to 16-bit, which means like the left shift 4-bit, and the advantage is the first one is convenient for math and compatibility. And second is no additional accuracy gain. So the just remember the pico like a WADC procession is just a 12-bit procession. It's not 16-bit. The 16-bit is just like when the MicroPython reads the like a voltage, it's just not expand the voltage the like a resolution, but the resolution is always like a 8 like a 0.8 micro like voltage. It's a 12-bit. It's not 16-bit. Yeah. Thank you for Xander to point this out. Yeah, I forgot to. Yeah, but he's not here. Yeah, you just thank here. Yeah, I forgot to mention it, but you just remember. Actually, the Pico W, it just has a 12 like a bit procession. Yeah, it's not a 16-bit, but it just like for the code, it just expand the procession, but the real procession is just a 12-bit. Any questions so far? Okay. So when you like do some other, maybe for the lab 4, you can now tell this very clearly, but for other labs, you may notice these differences. Okay, let's continue. So for today's lab, actually you can see the previous lab 4, we have the potentiometer, which means in the circuit you have two, everyone, just look at me. Yeah, you have two different like resistor, am I right? The potentiometer, which means you have, and for the capacitor, actually for this lab, we have the RC circuit, which means you just replace one resistor with one capacitor. Yeah, just like this. Yeah, and which means this one will be replaced with a capacitor. Any questions so far? Okay, let's talk about the capacitor. Have you ever learned the capacitor before? Yeah, what is capacitor? Actually, everyone knows the capacitor is only two isolated conductors together form a capacitor. Am I right? Yeah, actually, capacitor have different types. Yeah, like a titanium, aluminum, like a ceramic, and a trimmer thin film. Yeah, actually, many different capacitor, but the theory behind that is similar. Yeah. Okay. Yeah, this is a very typical like a chimeric capacitor. Like yeah, you can see those two like it's just two isolated conductors and isolated with this material. Yeah. Does anyone remember how this capacitor work?
Basically, there's a potential difference on each side of
Yeah.
the plates because one side is positive and
Yeah.
one side is negative.
Yeah.
And the negative electrons really want to go to the positive side, so
Yeah.
it creates a potential.
Yeah. Yeah.
Right. So, but then whenever, like say your switch is exposed,
Yeah.
all that stuff's going to get discharged and.
Yeah. You have the point. Yeah, like you can see when you charge, and one like the positive like positive well the positive like atom how to oh yeah the positive electrons yeah.
Oh, positive particle.
Yeah, electrons. Yeah, protons. Yeah, the positive protons like just get this part, this end, and the negative protons get this part. Actually, the middle materials. You can see what is voltage. What is voltage?
Like just like the force of the particles on how much they want to get to wherever they're trying to go.
Yeah. I think you get the point. Actually, the voltage just the difference. Do you remember?
Yeah.
Yeah. So you can see here is positive, here is negative. There is a difference, and this material, which make the negative cannot go to the positive part, and the positive part cannot go to the negative part. Yeah, but it can storage a field. Yeah, which means there are this material is a special material, and then you have a voltage for this capacitor. Yeah, this is a charge process, and the discharge is just like you can see this is this is just a battery positive, and this is a negative, and then there will be a current go through like this. Does it make sense to you? Yeah, this is just like it will connect to other different parts, for example, resistor or other and then goes to here, and then this one is just when it is discharged, it is just like a battery. That makes sense to you? Yeah, because here is a positive proton and here is negative proton. That makes sense to you? Yeah, so this is a capacitor. Actually, we have different types of capacitors. It has a similar thing. You can see this is a negative charge connecting, this is a positive charge. And you can see this like dielectrics, similar like the middle material. It will isolate the negative and the positive and has a voltage, yeah, like the potential, energy potential thing. And then when it is a discharge, charged, and the positive will get like here, and negative will have get here. And then when it discharge, and you can connect it to other resistor and other things, and it will have a current. That makes sense to you? Yeah, it's just like a battery. Any questions so far? Okay, and then okay, what is a capacitor for? Do you know? Yeah, you have already learned the capacitor. Actually, it can stores and releases electrical energy in a circuit. You can see when it is charged, the energy will be stored, and it also can be used for filtering and smoothing. Like, do you know the RC circuit? A very important like use for RC circuit is filtering, like low pass, high pass. Yeah, do you remember? Yeah, it's just for filtering and smoothing, which means it can denoise, remove some high frequency noise or some other things, and signal processing, and so on. Yeah, other functions. Yes, actually, the capacitors is very important for us. Okay, and then you can see for this like a circuit, this is the circuit we use today. Does anyone know how this circuit will charge and discharge? Like, did you read the lab instruction? No? Haven't? Okay, let me tell you. The GP16 will connect to the Pico, am I right? And when the GP16 connect is set to 1, what does that mean? Yeah, firstly, I forgot to, firstly, the GP60 is the output. Yeah, when the GP16 is set to 1, which means there is a voltage 3.3, am I right? And then it will charge to the capacitor. That makes sense to you? Yeah, and then after a long time, actually it's now maybe like 0.5 seconds, it will be charged. Yeah, and after that, I set the 16 to the 0. And then the discharging will be processed. Yeah, focus. Am I right? So how then what will happen?
The capacitor will discharge, like once the when the power gets set to 0, and then the AC will
Yeah, let me talk about like charging one more time. Yeah, this is charging. If this GP16 is output, am I right? When I set it to 1, it is 3.3, am I right? 3.3 volt, and it will have a current go here, am I right? And then actually it will like form a like circuit. Yeah, because this one and this one is just a measurement point. Yeah, ADC is just a measurement point, am I right? And when this one is when this point is set to 0 volt, and the circuit is still this one, am I right? And which means this will discharge, am I right? So it will go like this. Am I right? Yeah, because this is just the ground, and this is also like a connect to the ground like that. Yeah, so this is ADC is just a measurement point. It will like a measurement of the discharging voltage will become. That makes sense to you? Any questions so far?
So, okay, so whenever GP16 1, right, in this circuit, ADC 0 is 0.
No, actually the ADC will, like I said, the ADC 0 is just for measurement.
Yeah.
Yeah, which means when you give it a 3.3, and it will like a measurement this point, am I right? Yeah, and at the beginning, maybe this one is now like it's just from 0 increase to 3.3 like that. Yeah, and it will if you did not disconnect this, you always set it as 3.3, which means this voltage will go to a stable value. That makes sense to you? Yeah, until you set this is 0, this one will be so.
Okay. So when the capacitor is fully charged, it's going to read a stable 3.3 voltage.
Maybe not that accurate. Yeah.
So what is the capacitor?
You mean what is capacitor doing?
Yeah.
In a circuit? It's just for like a storage the like electrical and the when it charging, it will storage the you know like when it is when this capacitor is storage fully, it can be considered as a wear. You know that? Wear. Wire, yeah, there is no wire, yeah, wire, yeah.
Okay, yeah.
Yeah, when it is like a discharge, like a discharge, this one can be considered like a open connection thing. Yeah. Yeah. So which means this one, if you like a measurement, this one maybe it's 3.2, 3.1, but yeah, maybe not exact. But this one is now like at the beginning it's now 3.3. Yeah.
So, like initially, whenever you turned on the circuit,
Uh-huh.
the capacitor would begin charging.
Yeah, that's true.
And ADC 0 wouldn't be reading anything because.
Not anything. It will read.
Would it be receiving? Because, sorry, so, I mean, it's dependent on what the internal resistance of the ADC chip is.
Yeah, actually, let me ask you a question. What is ADC measurement here? Okay, it's just this one. What is this is ADC, am I right? What is ADC? It's just read the voltage here, am I right? Does it make sense to you? So it's a similar thing for this one. Okay? Yeah, for this one. If it is charging, it will continue to like a continue to like a if you read ADC here for now, it will from 0 increase. Let me talk about this one here. The capacitor charging, it will from 0 to maybe 3.3, maybe not 3.3, maybe around 3.3. Yeah, for the charging. That makes sense to you? And so, which means if you just this is 3.3, am I right? Actually, when you set this is 3.3, this capacitor will be charged, and then the voltage for this capacitor storage is from 0 to 3.3. That makes sense to you? To a stable voltage. Yeah. And then actually, if you don't set this GTCC pin to if you always set this GP16 to always 3.3, what will happen?
You always said what?
If you always set GP16 is 3.3, like a 1, what will happen? That it will not discharge, am I right? Yeah, it will not have this process. And the voltage is always this one, am I right? Until you discharge it. That makes sense to you? Yeah. So, any questions so far? Yeah.
So while this is happening, what would, I guess what I'm curious about is what is the graph that ADC0 is seeing, right? So like, if that's the voltage that the capacitor is seeing, what would be, like, what would go to ADC0?
Oh, actually, this is just you know, like the multimeter. Yeah, you have a circuit. You just connect. You just want to measurement the voltage in this resistor, and you connect the multimeter to one is one for this end of the resistor, and the other to the other end of the resistor. It's a similar thing.
So I guess then my question is, what is ADC0 measuring the voltage across? Like, is it measuring the voltage across the resistor or across the capacitor?
Capacitor.
Okay.
Yeah. That makes sense to you?
So that graph is what ADC0 would see.
Yeah. Yeah, this is just like how the ADC become. Yeah, like you, because you can see for the labs 15, you just you just print or save the data you read from the ADC. Yeah, actually the ADC is just the multimeter, because for the lab 4 we just use the ADC to create the multimeter. Yeah, it's just a multimeter to measurement the voltage here. That makes sense to you? Actually, yeah, it will have a current. Yeah, and the voltage is just similar with this one because it is parallel. When the circuit is parallel, the voltage will be same. You know that, am I right? Like, yeah, this is a very fundamental thing. Yeah. Furthermore, yeah, you have like this is for example, this is a resistor. All right, this is for example 3 volt and 10 k, whatever. And for this like circuit, what is the voltage in
It would be off.
it what?
All like, so.
Yeah, it will
across
be
the
3,
resistor-
right?
Yeah, it should be.
It will be 3.
Mhm.
And if you parallel one the other 10, what is the voltage for this one and this one?
Same.
Same, right? It's still 3. That makes sense to you?
Yeah.
Yeah, and yeah, so when the ADC, the ADC is just like a similar parallel with like a capacitor. That makes sense to you? Yeah. Any questions so far? Yeah, but you can see when you if this is your original, all right? If you just modify your circuit like this, thank you, and then the voltage for this tank will change, all right? Because it is in series.
Yeah.
Yeah, but parallel, it will be now changed.
Okay.
Yeah, that makes sense to you?
Mhm.
Yeah, okay. So the ADC is just like the connect a multimeter to measurement the voltage. That makes sense to you? Okay, so yeah, which means yeah, for this one, like it's the same thing. Yeah, once it is charged, and the voltage will change for in the capacitor will change from 0 to the fully to full. Am I right? And after you set the GP16 to 0, it began to discharge. Am I right? And from the full to the 0. Am I right? Yeah, this is just our like lab file. Yeah, actually, let's review it. This is the theory behind that. And in lab file, you will use Pico as a digital like voltmeter. Like we just talked about the ADC is just like a multimeter like that. Yeah, to try to measurement the voltage and record the voltage via time. Save data to a file, plot and fit a physics model And our goal is turn a microcontroller into a scientific instrument. Okay, this is lab 5. And then the big picture, in the previous lab, lab 1 to lab 3, now lab 4, the microcontroller controls the hardware. What hardware we control? Do you remember? Button? Yeah, LED. Yeah, this is all like different hardwares the PQW will control. Yeah, today like a microcontroller will measures physics, like measures voltage, and today's lab we will like there will some like electronics theory and programming thing and data science, because we want to save data. You will like if you review that you will see we will save data. And then physics modeling, we will try to analyze this data and to create it to fit some model. Yeah, you will know that. And for lab 5, you are doing is what engineers and researchers actually do. First, we will measure and then store and analyze and model. Yeah, actually for the lab 5, you just do what engineers do, or researchers do. Yeah. Okay, any question? Okay, then let's talk about the discharging and discharging capacitor again. Yeah, you can see here, this is our circuit, and this is our like hardware connection. You can see this one is just this one, this port. It will connect to ADC 0 to measurement the voltage here. Am I right? And then the capacitor will connect to ground, and then to from this pin and from this point it will connect to resistor and go to the GP16. Yeah, that makes sense here. And then if we set GP16 to high, it will begin to charging. It will begin to charge, and this is like a equation for the charge. And T, what is T here? Time. Yeah. Which means when as the time pass, goes on, and it will goes from 0 to the maximum, and this is a discharging, which means after we set pin 16 to low, and this V initial is just a full charge situation, and this is the equation for the discharging, and our like voltage, our like the VC, the capacitor voltage, will decrease from 0 from the initial to the 0. That makes sense here? Yeah, this is the equation. Yeah, you will use. Any questions so far? Okay. And then wait a moment. Oh, okay. What happens during okay. I think I forgot one more thing. If you review the lab 5, you know we will measurement the discharge. Am I right? We don't measure the charging. Do you know why? Do you know why we don't measure charging? We measure the discharging. Yeah, actually, if you observe it, you can see when we measure the charging, which means we need to when we set the pin to GP 16 to 1, we need to begin to measure. Am I right? Actually, this point is very short. Actually, you can see I draw this process is very long, but it will have very short time. It will around like 0.5 seconds. Yeah, which means like the code maybe is not that fast to deal with this process. Yeah, when you read this thing, maybe you read it from here. Yeah, and or maybe you just miss the whole process. Yeah, but the discharge you can see when after we charge, if we didn't if we don't set this is 1, it will always like keep this status. Am I right? Until you set this is 0. Am I right? And we are ready to measure and read this process, read this data. That makes sense to you? Yeah, that's the reason why we record discharge, not charging. Okay, what happens during discharging? Actually, you can see when like a capacitor discharging, like the voltage does not drop linearly. Yeah, it will just follow this equation. Yeah, and in this equation, the t is time, am I right? Yeah, you know that as the time passing and the voltage will change. What is the RC? The R is what? R is what?
10K.
10K. It depends on your circuit, but it's resistor, am I right? The C is capacitor, am I right? So when your circuit is decided, which means after you choose your resistor and the capacitor, your RC will be fixed, am I right? Yeah. So this RC we call it time constant. Yeah, because after you choose your RC, we call this tau. Yeah, this time this value is fixed. Yeah, and after 1 tau, the voltage will drop to 37%. Yeah, this is just like from many experiments. And actually, in our experiment, like the discharge takes about 0.5 seconds. Yeah, you need to find why. Yeah, I will leave this question to you. Yeah, but you can see the voltage does not drop linearly. It will drop follow this equation. Actually, this is an exponential equation. Yeah. Do you know what is linear? Linearly, yeah, drop linearly, which means you have a linear equation. For example, drop like this. That makes sense. But if this one is not like a linear, if you check this thing, you can see it's just like this. Yeah, that makes sense to you? Okay, let's continue to talk about that. Okay, hardware setting, sorry. And you will build an RC circuit and measure capacitor voltage. The important pins is GP16. Yeah, this is a charging control. You set it 1, it will charge. You set it 0, it will discharge. And the GP26 ADC 0, it is voltage measurement. Yeah, pico becomes a voltmeter. That makes sense to you? Yeah, any questions so far? No question? Okay. And what does the pico actually measures? Yeah, actually, ADC does not measure voltage directly. It measures, actually, I cannot, the ADC does not, it cannot read voltage directly. It just give us a 16-bit integer, this one. Actually, we have already learned this. We convert it to voltage. Yeah, this is just similar with lab 4. That makes sense to you? Yeah, okay. And then this is experimental procedure, like steps. The first thing you will charge capacitor and then release discharge, and then measurement the voltage every 1 milliseconds and see it to fail. You are recording a scientific data set. And let me ask you, why every 1 milliseconds here? Do you know why? Do you know why 1 milliseconds? Like why not 1 second? Why not 0.0001 milliseconds? Yeah.
We have to do with the order like magnitude of the time constant.
Yeah, that's true. Yeah. Actually, you want to read this voltage, am I right? Like read this voltage from this process. Actually, if you read it too fast, too slow like that, if you read 1 second, maybe you just mirror those 3 voltage. Yeah, it will not represent the whole process. If you like if this distance is too short and you measurement just it will not very efficient, time consuming, energy consuming like that. Yeah, actually, what's the idea for this one? Meaning, what's you know? Actually, we talk about actually this process is just like the first step. Convert the analog to the digital. What's the first step? Sampling. Yeah, sampling, which means sampling. We just get part of this signal. Do you remember? Yeah, the quantization is just this process like that. Yeah. Okay, let's let's continue to talk about. And then yeah, we have talked about this one. Okay. Writing data to a file. We store data in data.csv and then we analyze later. Real experiments always save raw data. And important rules is must write strings, always close file. Actually, I have already given you code. So, but you just remember, if you like try to save data to a file, you must follow these rules. Let me ask you a question. Why we don't like after we get this data, why we don't analyze directly? Why we want to save it to the file and analyze it later? Why?
So you can use it for like more than just one purpose, like if you wanted to, and it can be validated later by other people.
Yeah. That's one very important reason. Yeah, actually, huh? Repeatability? Yeah. Like similar like that. Yeah, that's a very important reason. Actually, there are some. Yeah, you can see the microcontroller. Actually, we know it has a microprocessor in that RP 2040, but the power is limited. Yeah, actually, if you deal with data, later you can use your computer, your own computer. You know your computer is very powerful. Yeah, so the microcontroller like slow at plotting and analyze things. Yeah, the computer fast at plotting and analyze things. So the workflow is you use Pico to connect data, and then you use computer to analyze data and plotting. Yeah, that makes sense to you? Yeah, actually, this is real energy engineering workflow. Actually, if you do research, if you do if you even in the future you work in some companies, in many situations you just connect the data firstly, and then you use your computer, some tools, some software to analyze this data. Yeah, I don't know if you have some internship. I think if you have, maybe you follow this similar process. Yeah. Okay, let's continue. Okay. Timing the measurement. Yeah, we use actually in this lab, we use a new function. Like this is takes us, like this is just the time now, the computer time now, like the microcontroller time now, or like a computer time now. And this is the difference, like time. Yeah, this is prevent overflow errors. Yeah, normal time functions breaks in fast measurement. Yeah, this is, I just talk about why we simple every 1 minute a second. Too fast, memory fails, Pico crashes because, yeah, it's not efficient. And too slow, lost details. Yeah, am I right? Okay, any questions so far? Okay, and then plotting the data. Yeah, we switch interpreter. Yeah, from local Python to local Python 3. Actually, when we plotting, when we plotting, we will use some function, and I just upload some materials into the reference in Blackboard. If you found there are some libraries you haven't installed, but you don't know how, you can review that materials. Yeah, document I have already uploaded to the Blackboard, and then read the CSV, plot, scatter, add a model curve, and we compare measurement to theory. Actually, you can see we read the voltage using Pico, am I right? Also, we have RC. We can like use this equation to calculate it, am I right? Yeah, so we can compare those two. Yeah, one is measurement, the other is calculation. Am I right? So if it is right, the data overlaps curve, which means those two will be very close. Otherwise, you may need to check what's wrong with your code or circuit. That makes sense to you? Okay. And then this is curve fitting. Actually, you can see in our like if we for the in the real application, we actually mostly we don't know the RC in a specific circuit. Like this circuit maybe is a black box. Am I right? We don't know that. So, but we know like the input output. Am I right? We know this equation, so we can like calculate this tau. We don't, but we don't guess tau manually. We will compute the beta tau using optimization. Have you ever heard of optimization before? Like linear fit, you have some data and you use those data to get some parameters for you. Yeah, this is like a optimization. Yeah, we will like use the similar thing. Yeah, we will obtain best top. Here is idea uncertain. Actually, this here the point 0002 is idea for uncertain, because when the programming to give you the tau, there will be uncertain. This uncertain will tell you how well we know the measured value, because this like a tau, the like a optimization method give you, maybe it's not that accurate. Yeah, because your measurement maybe is not like that accuracy. I'm right? That makes sense to you? Any questions so far? Okay, and yeah, this is a real experimental sense. Okay, what you will demonstrate today? Yeah, working circle, CRSV data, plot, fitted curve, internal ADC reading thing. Yeah, and then the key concept summary. We will have ADC measurement, sampling interval, data logging, and exponential decay and curve fitting. Experimental validation. Yeah, this is the lab for today. Okay, this is some common mistakes. Yeah, you need to avoid. Yeah, not charging capacitor long enough. Yeah, because if you charge it long enough, maybe it will have some circuit like a affection thing. And a wrong pin, you need to check your pin very carefully. A wrong voltage conversion, and sampling too fast or too slow, and forgetting to refresh files. Yeah, like sometimes some students save file and they found out something wrong, and they will like run the circuit again, but they forgot to remove the original data, the old data, and then you will find the result will be very weird. So you need to pay attention to that. Okay, very excited day. Final project. Yeah, actually, I don't know why today many students are not here, but we have a very excited final project. Yeah, in our final project, each group will design and build a microcontroller-based assistive device that helps a user with cognitive difficulty complete a daily life task safely and reliably. Yeah, and then we will have 16 students total, and then 4 students, one group, and I will like give you the group later. And the group, yeah, the 4 students per group. All groups work on the same general topic, medication, like daily routine assisted system. However, each group is responsible for a different real-world scenario. Designs must address the assigned user limitation. Okay, let's talk about the group A, hearing impaired user. The user cannot reliably hear arms, because some people, some dimension people, they cannot hear. Their hearing is something wrong. Yeah, system requirements. Visual feedback must be the primary, like a notification. Multi-level urgency indication, like color, brightness, flashing pattern, must still function in a bright room environment, because mostly in the like bright room environment. And the design challenge, how to guarantee the user notices the reminder without sound. Yeah, and this is group A. And group B, vision impaired user. Yeah, some users cannot like read screens or small text. The system requirements, audio or variation-based feedback required. And a simple interaction, no menus. Confirmation feedback must be non-visual and distinguishable across multiple situations. And design challenge, avoid confusing interaction steps. Yeah, this person like maybe has vision impaired user. And the group C, frequent force operations user. The user frequently presses buttons unintentionally. Yeah, system requirements is like force trigger detection. Confirmation logic, like long press, double press, timed confirmation. The system must provide like accidental like task competition. And design challenge, balance usability via safety. Yeah, because you can see sometimes you need to check if it is normal. Yeah, normal situation or just a miss operation. Yeah. And then D, memory loss or repeated action user. The user may take medication twice in a very short time. Yeah, this is normal. The system requirements prevent duplication, confirmation within time window. Track last computation time, like provide a warning when repeated action detected. Design challenge, like design reliable stick tracking and timing logic. Yeah, and then let's compare. This is for group, and group one, group A, hearing impairment, B, vision impairment, C, force operation, D, repeated medication. Yeah, actually you can see different group have different like type difficulty. Yeah, the A like interaction design have something like a difficulty in the interaction design, and the B is information encoding, and C is robust logic, and D state and time modeling. Actually, also different groups have different real challenge. Ensuring, yeah, A, ensuring the user notices alert, and the B, covering meaning through some patterns, and the C, determine user intent. D, like verify real human action, like common mistake, like yeah, you can notice that, and engineering skill development, like human-centered design, and B, interface design, C, like embedded reliability, D, system modeling. Yeah, you can see, actually, for group A and B, may look simple, but require careful design thinking. Yeah, because you need to design different situation. Yeah, different, like many different situations for the like hearing impairment and the vision impairment. And group CD may look complex, but many programming complexity. Yeah, that makes sense to you. So, I know most students give me that survey, and I will like 4 students, one group, and then after I give you the group situation, and you need to tell me which topic you want to choose, and but first come first get. I'm right. Yeah, if you some other group choose one topic, and that will be removed. Yeah, that makes sense to you. Yeah. Okay. And this is today's class. Any questions so far? Oh, one more thing. And we will start this class still from 1 o'clock. So if you are free from 1 o'clock, you are welcome to come here to finish the lab earlier, because I have only today I have some family thing to deal with, so I need to leave at 4:15. Yeah, 4:50. Yeah, 4:50. Yeah. So hope we can finish today's lab as soon as possible. Yeah. Any questions so far? Okay. Yeah.